Welcome to our third video in our Class 20 series of lecture videos. We ended the second video with a nice line drawn in our notes saying that material above that line may go on midterm 2. So here we are in our third video. We're looking at material below that line. We still, yes, need to be familiar with SN2, SN1, E1, and E2-like reactions if we encounter them in this material. But other specific topics like epoxide opening, I don't believe you will see in your practice midterm 2 material. So let's look at epoxide chemistry, and specifically, let's look at epoxide opening. Let's say we have ethylene oxide and we throw in sodium cyanide in a nice polar aprotic solvent. We do an SN2 reaction. In fact, our cyanide nucleophile kicks out on alkoxide. This is a rather strong base, maybe not a great leaving group. So why is it okay this time? And after that SN2 reaction, we could treat it with an aqueous acidic workup, so a little H3O plus and Cl minus, and we get this alcohol. Normally we don't see alkoxides as leaving groups, but this reaction is driven by the release of ring strain. That's a 3-membered ring, so there's about 27 kcals per mole in it. And so that's why this is actually favorable, because we release that. Of course, the carbon bonded to the oxygen is electrophilic. Both of those carbons are electrophilic. We can write dipole arrows that suggest they are electropositive. So let's look at asymmetric epoxides. So what do I mean by asymmetric epoxides? Well, with ethylene oxide, we had a CH2 on either side. This time, we've got a CH2 and a carbon bonded to 2 methyl groups. So there are 2 possible regiochemical outcomes if we were to try to react this with a good nucleophile, like sodium methyl sulfide in our nice polar aprotic solvent, DMSO. And in fact, our nucleophile would prefer to attack the least hindered carbon, because this is SN2, and that is what we see. We see that nucleophile opening up that epoxide by attacking the least hindered carbon. After aqueous acidic workup, we get this tertiary alcohol. Only one product, so attack of the nucleophile of the least sterically hindered carbon is the preferred method. Similarly, you could actually open that epoxide with lithium aluminum hydride. It would deliver a hydride as a nucleophile. And in fact, after aqueous acidic workup, we would create tert butyl alcohol. So we don't usually see hydride as a nucleophile, but LAH will give us our hydride as a nucleophile for epoxides. You could similarly add a deuterium atom this way if you used lithium aluminum deuteride followed by aqueous acidic workup. We can't really use sodium borohydride to open up epoxides. It's just not strong enough. So if we can add in hydrides as nucleophiles, could we open epoxides with Grignards? And of course, if I'm asking, the answer is probably yes. So Grignard reagents will open epoxides. Here we have our asymmetric epoxide. Of course, our methyl magnesium Grignard adds the methyl to the least hindered side, and after aqueous acidic workup, we get this tertiary alcohol. Similarly, for this epoxide, we'd add the methyl magnesium bromide Grignard. We'd add that methyl carbanion into the least hindered side, and it would be an SN2-like process. So the methyl group is on the opposite side of the ring as the hydroxyl group in our final product, because it had to attack from the back side, pushing the hydrogen on that carbon up. Mechanism, here we go, right? Here's our methyl magnesium bromide. We're taking these 2 electrons, pretending that they belong to the carbon, using them to form a bond to our least hindered carbon, and opening the ring to this magnesium alkoxide bromide salt, which we protonate with our acid in the following step. So epoxides are useful 2-carbon synthons. If we had to decide how we might think about making this alcohol, we could think about cutting bonds either across A or B. If we said A, we would have to use this homobenzyl magnesium bromide Grignard reagent and formaldehyde to extend it by a CH2OH after aqueous acidic workup. This is kind of an unusual reagent. I couldn't necessarily buy this. Or we could simply use benzyl magnesium bromide and ethylene oxide. Both of these are commercially available. This would be a much easier route. So decision B would be the preferred route. That pretty much finishes up this particular video in our Class 20 series of videos. Good luck with the problem, and I'll see you on the next one.